Alagu Parvati, Associate Professor of Physics. I am going to discuss about formation of Newton's rings and its application in determining the wave. First, let us see how the Newton's rings is formed. To form a Newton's ring, we have a plain glass plate over which plano-convex lens will be placed. At the point of contact of a plain glass plate and plano-convex lens, there is no air film. So at that point, thickness of air film will be 0. As we move from the center towards Q, the thickness of air film goes on increases. So we are getting circular rings because of the interference between the reflector rays from the bottom and top of a air film in between the plain glass plate and a plano-convex lens. Here we are using a monochromatic source. When a monochromatic source incident normally on the plain glass plate and a plano-convex surface, there is a interference pattern occurs between a ray reflected from the bottom of the plain glass plate and the top of a plano-convex lens. Due to the interference, we are getting a circular fringes. These fringes have a same radius. The same thing will be discussed in this slide also. Now let us see how to find out a radii of a ring. To find out a radius of a ring, now at O is a point of contact between a plain glass plate and a plano-convex lens, and A be the center of curvature of a plano-convex lens and R be the radius of curvature of a plano-convex lens. We are completing a circle with the A as a center and R as a radius of curvature. So here this at a point C, dark ring will be formed and thickness of a air film at that point will be T, and the radius of a ring for a dark ring is CB and it will be RM. We are using a geometry of a such as dB into BC is equal to EB into BO. So here BC equal to DB. So DB into BC will be RM squared and EB into BO will be 2R minus T into T. Here the thickness will be very less, so we can neglect compared to a radius of curvature. T will be small, so the TR minus T becomes 2R. So from that we can find out the radius for a dark ring. Already from the theory of interference we know that the condition for dark ring is 2nt cos R is equal to m lambda. Here the light will fall normally on this system, so R will be 0, so cos 0 will be 1. So the equation becomes 2nt is equal to m lambda, where m takes the value of 0, 1, 2. Now from that relation we find out the T, and that T value will be substituted in equation 1. We are find out the expression for the radii of a dark ring as a RM or m lambda divided by n. Now this RM squared we have calculated. RM will be square root. So the radii of a dark ring is proportional to the square root of a natural numbers. So to find out the radii of a bright rings, now we have take the condition for to formation of a bright ring. Let it be 2nt cos R is equal to 2m minus 1 into lambda by 2. Here we substitute that relation in equation 1 and we are find out the thickness of air film for a dark ring, and this will be substituted in first equation. We are getting a radius of the bright ring as 2m minus 1 into R lambda by 2n. So the radius of the bright ring will be proportional to a square root of odd natural numbers. Since we have determined the radius, we can find out the diameter of the bright ring. The diameter is nothing but 2 into Rm. So we substitute in that relation Rm and we are find out the diameter of a bright ring as square root of 2 into 2m minus 1 r lambda by square root of n. The same procedure we are find out the diameter of a mth dark ring as dm is equal to square root of 4m r lambda divided by square root of n. Now we have derived the relation for a diameter of the bright ring and the diameter of the dark ring. So experimentally we can find out the radius of a bright ring or dark ring. Also from that we can determine the wavelength of a source used. For that the experimental setup is we have a plain glass plate and plano convex lens, and we have a monochromatic source and we have a convex lens. The purpose of the convex lens is to have a parallel beam of light. The parallel beam of light falls on the glass plate which is kept at an angle of 45 degree. When a parallel beam of light falls on this 45 degree glass plate, it will be reflected normally on this plain glass plate and plano convex lens. So this light interfere with the thin air film between these two surfaces and we are getting a bright and dark fringes that will be viewed through a microscope. So now then the microscope will be adjusted such that at the center of a crosswire we are a dark ring, and now the microscope will be moved towards left or moved towards right such that we make the crosswire to be tangential to the 21st dark ring, and we have to take the microscope reading. Then the microscope will be moved towards 18th dark ring, then 15th, 12th, 9th such that we are reaching a center. The same each time we have to note the microscope reading, and then it will be moved towards the left towards 21st dark ring, then 18th, 15th, like that again we are reaching this center. So from that we can determine the diameter of a dark ring using a microscope. Then that readings are tabulated for left and also right. If you subtract the left and right reading, we are getting a diameter of the ring. Then we square that, we get a d squared, and from that if you find out for the difference of mth and pth reading, we can find out dm squared minus dp squared. The last column will be constant. From that we can find out the radius of the ring. Next we can find out the lambda using that relation. For the pth dark ring we have a diameter relation. For a mth dark ring we have a diameter relation. If you subtract these two, we can find out lambda, the wavelength of a monochromatic light. So the wavelength can be determined from the tabular column, and the radius of curvature of the lens can be found out using a Boyce method. Suppose if you know the lambda, then we can also find out the radius of the ring. So using Newton's ring experiment, we can find out the wavelength of a monochromatic light. Thank you.